Hi, my name is Chris Andrews. I'm the COO and head of product for Rendered.ai, and I'm here to talk to you today about the use of synthetic data for training remote sensing AI. My background is in the geospatial industry with about 25 years at companies such as Esri, IBM, and Autodesk. Most of my career I've focused on practical applications of geospatial for end users who need to solve other problems and aren't typically worried about the GIS. Uh, I got into 3D about 15 years ago and have worked on 3D applications for defense, AEC CAD BIM, urban planning, and many other applications since. I joined Rendered AI about a year and a half ago to help shape the story and solve customers' problems by applying 3D to synthetic data for the purpose of helping train and improve algorithm development across the computer vision industry. Rendered AI offers a cloud-hosted platform that is intended to help customers generate data when they can't otherwise get data for training algorithms in artificial intelligence and machine learning. We were established in 2019 in Bellevue, Washington, in the States. We offer a subscription model in the public cloud that encompasses 2D and 3D content creation, simulation design, and data generation. And generally, we tend to be the shortest path between a customer's AI problem in which they're having trouble finding or sourcing data and solving and helping them train their algorithms. Typically, we focus on computer vision applications that particularly need physically accurate simulated sensor information. We can generate a wide variety of other data in the Rendered AI platform as well. One of the things that we've observed in working with our customers is that they may come to us with a problem today that we can help them solve. Their AI problems always change, meaning that the data that they need to train their AI always changes as well. Typically, you know and we hear that there are tremendous barriers limiting the adoption of AI across the industry in a variety of cases, especially in the computer vision arena. Real data can be expensive, unavailable, or even impossible to acquire and label. Real data can only capture what can be observed in the wild. So rare objects and scenarios can be very hard to capture in inadequate types of real data or quantities to train algorithms. In some cases, customers are deploying a new sensor in the field or planning to take on new data types that they haven't worked with before. And if they don't have examples of that data, they can't experiment and innovate. And finally, data labeling itself is inaccurate and imprecise. And in worlds like the defense world, where you may be using synthetic aperture radar, multi and hyperspectral imagery, and a variety of other content that's not just simple visible light imagery, data labeling can be very difficult for humans who aren't naturally able to interpret some of those more distant wavelength domains. It's been observed by multiple people that 85% or more of data that is being collected today is unstructured, unlabeled, and not ready for AI. And what we see with increased amounts of deployment of small sensors at the edge, many more Earth observation satellites being thrown in the sky every day, that the amounts of the amounts of the amounts of computer vision content that will need to be processed in the future for real intelligence here on the ground are just going up and up and up. Synthetic data has the potential to solve the AI data problem. Synthetic data is engineered data that AI interprets as real data. Here at Rendered, we actually build a platform as a service and developer framework for customers to be able to generate their own custom synthetic data channels that can output the computer vision content that they need to solve their problem. We're essentially trying to fulfill this statement that Forbes is making, which is that Essentially, data is one of the world's most valuable resources, and we can help customers generate it cheaply and quickly in unlimited volumes. Typically, what we find is data scientists today are focused on acquiring or scraping together whatever data they can get, training algorithms based upon that data, testing the algorithms, maybe tweaking them a little bit, and then just accepting or rejecting the results. This process tends to be unpredictable and expensive. It can be very difficult to train algorithms on inconsistent data. The, the testing requirements for using real data only actually requires you to partition your data such that you can't even use all of the real data to train. And the results tend to be limited to just you get what you can. We are already observing that tomorrow's AI workflow incorporates synthetic data in an iterative, continuous cycle that allows initial experimentation to develop data that actually works for the customer's initial problem, and then allows a comparison for things like also using real data sets, but also migrating that data by improving data generation over time so that additional problem sets can be solved. Synthetic data tends to be inexpensive. You can generate unlimited amounts of it in the cloud. Synthetic data is 100% accurately labeled. Real data sets can be used with synthetic data for comparison and post-processing, and data can be designed for edge or impossible cases and for things like removing or even testing for bias. Rendered AI's solution has two major components. Underneath the customer experience is a platform as a service that incorporates standardized tools wrapping cloud capability for things like creating and configuring jobs, executing jobs in large quantities, accessing data sets that build up over time, post-processing data sets to do things like calculate analytics or even apply something called domain adaptation to help synthetic data sets appear to be even more like real data sets. And then the platform actually allows headless integration into other systems so that you can even configure and generate synthetic data headlessly without being in the Rendered AI web experience. On top of the platform as a service, we offer a variety of custom and pre-configured vertical applications and scenario configuration capability, and in a variety of domains, including some of those that you see, and in an expanding number of domains every day. One of the most relevant examples of what we've done to help customers is, and actually one of the more popular types of data that is generated using Rendered is synthetic satellite RGB imagery for purposes of object detection. Typically, our customers are using Rendered in this way for generating not only just images of rare and unusual objects in the field, but in some cases, complicated scenarios of those rare and unusual objects in which the scenarios may have specific meaning and which may only occur at extremely rare times and thus are hard to capture in quantity for training algorithms. In fact, Dstl, with the help of Faculty AI, has actually already explored use of Rendered AI on a project involving testing to see whether a particular type of satellite imagery would work for a specific detection scenario. We have multiple enterprise and developer subscription customers using Rendered for this type of data. It's highly repeatable. We can do things like help the customer vary sensor resolution and angle. You can use Rendered to customize object placement, and we've even seen some interest in using services such as ArcGIS imagery services. We have partnered with the Deers Lab out of the Rochester Institute of Technology to be able to actually wrap DeerSig, their US government-supported simulator, in Rendered and make it available through our web interface. This is a unique relationship with the RIT in which Customers who access DSig through Rendered actually don't have to have training in DSig. Uh, this can give customers access to multispectral, hyperspectral, and other radiometrically accurate information that can be output from DSig. You can validate using calibration panels, and we've also engaged for some customers with third-party validation using real live physicists. And you can actually get pixel-level geospatial accuracy. We also have built our own synthetic aperture radar simulator, which can be used to generate individual imagery chips. We are actually working on increasing the scene complexity and scale that is possible with our simulator. It basically just takes an exponential amount of cloud compute resources. We have this available for enterprise and developer subscription customers to explore. It's experimental. Synthetic SAR tends to be the bleeding edge of the bleeding edge. But one thing about SAR is that it is not human readable. So human labeling can be pretty much impossible. And having synthetic labeled SAR is ideal for training algorithms to search the large amounts of SAR information that are being collected today. Another application of Rendered that was done by a customer called Big Bear AI for the US Navy was to actually generate synthetic images of ships at sea to emulate drone-based data collection. In this case, the customer needed the ability to place a variable number and types of objects, actually in some cases detect components of the ships. So in many cases, the annotation indicated specific parts of ships. And then the customer needed to be able to do this in variable weather wave and with other types of obstruction characteristics. We've also got applications in the kind of co-registered imagery space. In this example, this was a fixed mount multi-camera FMV application capturing both thermal and RGB imagery for border crossing type case in which there were people, animals, and vehicles all moving. We also work with a variety of partners. We can't build all the content or create all the simulators ourselves. In this case, we actually have partnered with Prestigious out of Canada to have access to their extensive model library of 3D assets. We expect to partner with others in the future for similar types of content in other domains. And often this content is available through our subscriptions on request. Another specialty that we have is the ability to use a studio team to build extremely large synthetic environments. As you can see, these environments can be everywhere from in city centers to polar and Arctic cases to remote desert and many other types of environments. We can do this with a combination of reality capture data, conventional modeling, and even using generative techniques. I'm going to take a quick second and show you how things work in the Rendered.ai platform. All right, so here I am at the landing page in my Rendered.ai instance, which you can access right from the Rendered.ai website. Anyone actually can sign in and request an account and try out demos, including this SAT-RGB demo that we have. In this case, you can see in my organization, I've got a variety of workspaces, which are basically projects that allow me to organize content for different applications. In the case of the satellite RGB content that I've been talking about, we've got a workspace set up that accesses a synthetic data channel for generating RGB satellite imagery. And here I have a variety of graphs that allow me to configure jobs for synthetic data generation. For example, I'll pop open this job and you can see that what I've got is a variety of ground vehicles placed in a parking area, staging area, and that image is generated by configuring a variety of objects in this edge node diagram. For example, you can see that we've placed an Army truck and a Bradley. They're being chosen randomly. There are variety of rust, dent, and other modifiers on these trucks. You can see that I have actually got control over how these objects are being placed in a rectangular grid. And then you can see that they're being placed in parking areas, which I could change the parking area, for example, including just selecting one randomly. And you can see that I've got a simple RGB sensor where I can set the GSD and other attributes. And then this is all brought together in a scene assembler and then a renderer. From this part of our application, you then can stage this graph, come over to the jobs panel. We can see the job that I just staged. You can see that there were other jobs that were run in the past. And if I want to, I can then kick off this job. I can even change the name and run. You can see the job is queued up. There's an interface for monitoring it. There's also a headless interface for accessing this through SDK. And what you see at the end of the result is a variety of data sets that get generated. These are all data sets that have been generated in the past. When I look at a data set, for example, I can see individual data items. And I can also do things like add custom annotation and even use what's called UMAP analysis for comparing multiple data sets and seeing if they are actually behaving in the same feature domain space. For the sake of illustration, I'm going to show you that we can also have UMAP analyses, which allow us to compare synthetic and real data sets. In another workspace, I've got a UMAP analysis that actually compares 3 different types of synthetic satellite imagery. So this interface allows us to see how closely each of these 3 data sets appears together in an abstract feature space that is created from running the data sets through the UMAP algorithm. And what you can see, for example, is that many of the images that are isolated out here on their own are from a data set where the time of day is extremely early in the morning. The other 2 data sets appear in more similar feature space. Even though one data set is RGB and the other is panchromatic, they are both more similar than either is to the other RGB data set. Okay, so that's about it for our demo. From here, of course, you could download data sets, use them to train your own algorithms, and then create more workspaces and graphs to organize additional content for synthetic data generation. All right, so that'll be it for me. Thank you very much for your time today. Again, I'm Chris Andrews with Rendered.ai, and it's been my pleasure to be able to present to you here at the Dstl AI Fest. Thank you.